Hello everyone, I'm Sai, and today we present online language splatting. This work is in collaboration with University of Delaware and Bosch. As shown in the video, the robot traverses abandoned buildings and maps the surrounding areas and interacts with the responders to aid in finding the victims and objects. Real-time interactions are crucial for robotics and AR applications. For real-time interactions, mapping is crucial. Gaussian splatting enables efficient photorealistic 3D mapping. Imagine a robot navigating an environment. A human says, "Find the first aid kit." And the robot, to succeed, it needs to find it. So, given the current methods, they are too slow, takes minutes per frame. This motivates our research questions. How can we build a real-time photorealistic mapping system that also understands natural language commands? Most existing approaches combines clip with SAM. This pipeline is powerful but far too slow for real-time applications, since each region has to be processed separately. And our idea is to instead make use of clip pixel-wise. That means every pixel in the image directly carries a language embedding. From a single image, we can immediately generate a language map. There's no extra segmentation needed. This runs extremely fast, about 12 milliseconds on a low-end GPU like a 2080 Ti. Here, you can actually see the response of the map for the query vase, where the correct regions lights up immediately. While this gives us fast real-time maps, the boundaries are still not sharp enough, and that brings up second step. To address the low resolution issue, we designed a simple yet effective super resolution decoder. It takes the low resolution clip feature maps, fuses them with the hierarchical image features, and outputs dense, high quality language maps. Together, the encoder plus the decoder runs in just 14 milliseconds. Below you can see the improvement. Before, the response for a vase was fuzzy, but after that the object boundaries are very sharp. Here we integrated our module into Gaussian splatting SLAM system. On the left, you see our result. We generate dense, high quality feature maps at a fraction of a cost compared to LangSplat shown on to the right. Our current runtime is 0.8 seconds per frame, which is already 200 times faster than LangSplat. With the even much faster SLAM systems, we can push this runtime even further down while keeping the same level of quality. The second challenge we face is memory efficiency. Language embeddings are very high dimensional, around 768D. Embedding these into millions of Gaussians is infeasible. So we designed two-stage compression technique. First is offline stage, which compresses 768 to 32D, which is trained offline. And in online stage, we compress even further from 32 to 15D, which adapts to new scenes. This allows us to embed low dimensional features into Gaussians, saving the memory while maintaining the accuracy. Results on the right show that our two-stage approach improves overall performance compared to using a single stage. The third challenge we face is how to jointly optimize color and language in Gaussian splatting. In prior methods like LangSplat, color and language embeddings share same Gaussian parameters, such as rotation, scale, and opacity, which is shown to hurt the image quality when jointly optimized. Because language features are homogeneous, for example, large walls and areas may all share the same language code, which conflicts with the fine details needed for the color. And our solution is to decouple these parameters. We keep separate modes of rotation, scale, and opacity for color and language, but still share same position. And this seems to produce more sharper rendering details. Here are the visual results of our approach. Using the disentangled optimization, we are able to produce sharp images. By having a separate opacity, rotation, and scale produces the highest image quality as shown in the table. We now describe the overall pipeline. RGB images are passed to pixel-wise clip encoder to produce pixel-wise language maps, which are then upsampled by super resolution decoder to produce dense and high-quality feature maps, which are then compressed to a lower dimensional using a two-stage encoder in an online fashion, and then embedded low-dimensional code into the Gaussian mapping, where language and color are optimized using our disentangled optimization strategy. And when user queries for a text, we take the language, we render the language map and pass to the decoder to recover the full clip dimensions, and then perform a similarity between the text and the feature map to find the object. We not only achieve better performance, but also we are 40 times more efficient, and our proposed modules are light and runs more than 40 FPS. Here are some more qualitative results. Ours is indicated to the left and Langsplat to the right for the word carpet. And this result is for the word indoor plant. We also evaluated our pipeline in 3D, and we are able to identify the query of these objects well aligned to the ground truth while performing online. In summary, we present the first online language splatting SLAM system, which is fast and flexible, 40 times more efficient than prior methods. Lightweight modules operate at 40 FPS in practice, can easily integrate with the current state-of-the-art SLAM systems. Feel free to check out our website, code, and paper using the QR code. Thanks for your attention.